For decades, the story of the universe's origin has been one of the most beautiful and elegant narratives in modern science. 13. 8 billion years ago, everything that exists, all of space, all of time, all the matter and energy, was compressed into a point smaller than an atom. And then, in an instant beyond our comprehension, that point exploded outwards in what we call the Big Bang. Since then, the universe has been expanding, cooling, organizing itself into galaxies, stars, planets, and eventually conscious beings able to look back and wonder how it all began. It's a near-perfect story, mathematically elegant, observationally verified, philosophically satisfying. And now, at this precise moment in history, that narrative is starting to crumble. Not because scientists were lying, not because the data was fabricated, but because the universe itself has just done something it shouldn't be able to do, according to our most fundamental equations. It's showing us two incompatible realities at the same time. And the most unsettling thing is, both realities are backed by extraordinarily precise measurements made by the most advanced instruments humanity has ever built. We're living through what cosmologists, with almost comical understatement, call attention. But it's not just attention, it's an existential crisis for the standard model of cosmology. It's the moment the universe stopped playing by our rules. Let me explain exactly what's happening. To understand the crisis, you first need to grasp how we measure the speed at which the universe is expanding. Imagine you're in a dark room and someone lights candles at different distances from you. If you know exactly how bright each candle is up close, you can calculate how far away it is simply by measuring how dim it appears from your position. This simple principle is exactly how astronomers measure cosmic distances. We use celestial objects whose intrinsic brightness we know, we call them standard candles, and by measuring how faint they appear from Earth, we can calculate their distance. Type Ia supernovae, extremely specific stellar explosions, are the most reliable standard candles we have. But here's the crucial part. We don't just need to know how far away galaxies are, we also need to know how fast they're moving away from us. And we measure that by observing how their light is redshifted, a direct effect of the expansion of space itself. When you combine both measurements, the distance and the recession velocity, you get an incredibly important number called the Hubble constant. This number describes how fast the universe is expanding right now. It's not just some academic data point. It's literally the rate at which the fabric of space-time is stretching. It's one of the fundamental constants that define the physical reality of our universe. Now, there are two completely independent ways to measure this constant. The first, called the cosmic distance ladder method, uses precisely those standard candles we talked about. You observe supernovae in nearby galaxies, then, in more distant galaxies, building a step-by-step ladder out to the edge of the observable universe. With this technique, you get a value for the Hubble constant of about 73 kilometers per second per megaparsec. Now, if that figure means nothing to you, don't worry. The important thing is the number, 73. The second way to measure the same constant is completely different. It doesn't look at current stars, it looks at the oldest light in the universe. Nearly 14 billion years ago, when the universe was only 380,000 years old, the first neutral atoms formed, and light was able to travel freely for the first time. That primordial light, stretched by cosmic expansion into microwaves, still fills all of space. It's what we call the cosmic microwave background, or CMB. It's literally a baby picture of the universe. And that picture contains incredibly precise information about the initial conditions of the cosmos. By analyzing the tiny temperature fluctuations in that background, we can calculate exactly what the early universe was like, and using our best theories of physics, project how it should have expanded to today. This method gives us a value for the Hubble constant of about 67 kilometers per second per megaparsec. 67, not 73. Now, you might think a difference of 6 units isn't a big deal. After all, we're talking about astronomically difficult measurements across billions of light years. A small measurement error would be perfectly understandable. But here's the problem that keeps cosmologists up at night. These aren't measurement errors. Both values are extraordinarily precise. The error bars, the margins of uncertainty, have been shrunk so much that we can now say with over 99% confidence that these two numbers are genuinely different. It's as if two architects measured the same building with the most precise rulers ever made, and one said it's 73 meters tall, while the other insists it's 67 meters tall. Both are experts. Both use instruments calibrated with extreme accuracy. Both repeated their measurements dozens of times, but their results are irreconcilable. What does this mean? It means one of two equally disturbing things. Either there's something fundamentally wrong with one of our measurement methods, something we haven't detected despite decades of refinement, or there's something fundamentally wrong with our understanding of how the universe evolves. And this is where the most extraordinary instrument ever sent into space comes into play. The James Webb Space Telescope, launched in December 2021, was designed specifically to see farther into space and farther back in time than any telescope before it. Its primary mirror, an almost miraculous feat of engineering, is 5 meters in diameter compared to the Hubble's 4 meters. But more important than its size is its ability to see in the deep infrared. Why is this crucial? Because the light from the most distant galaxies has been stretched by cosmic expansion for so long that it's no longer visible light. It's become infrared radiation. James Webb can see that light. It can see galaxies so far away that their light has been traveling towards us for over 13 billion years. When they turned the telescope on and pointed it at the deepest regions of space, astronomers expected to see something beautiful but predictable. Early galaxies, small, chaotic, barely forming in the primordial soup of the young universe. Instead, they saw something that shouldn't exist. Massive, structured, mature galaxies with billions of stars already formed, at times when, according to our models, the universe was barely old enough to create something so complex. It's like digging for the first human settlements and finding perfectly constructed glass skyscrapers instead. The timeline just doesn't work. One of the most unsettling images shows galaxies that, according to their redshift, existed when the universe was only 300 million years old. 300 million years sounds like a long time, but on cosmic scales, it's a blink of an eye. According to the standard model, at that time, the universe should have been filled with the first primitive, massive, chaotic stars, still merging into shapeless proto-galaxies. But what we're seeing are galactic structures that look like they needed billions of years to form. It's as if someone fast-forwarded a time-lapse video, except it's not a video. It's the physical reality of the early universe. Theoretical cosmologists have been scrambling to adjust the models. Maybe the first stars were more massive than we thought. Maybe galactic formation was more efficient in the early universe. Maybe there are mechanisms we don't understand that accelerated the aggregation of matter. But every tweak you try to make to explain these impossible galaxies creates new problems elsewhere in the model. It's like squeezing one end of a hose to stop a leak and creating 5 new leaks somewhere else. The standard model is under immense pressure, and the cracks are starting to show everywhere. Now let me take you even deeper into this crisis. For decades, we've known there's something strange about the composition of the universe. If you add up all the visible matter, all the stars, all the planets, all the gas, all the cosmic dust, it only accounts for about 5% of the total density of the universe. The rest is divided between two completely mysterious components that we've never directly detected. 25% is something called dark matter, which doesn't emit light but exerts gravity and seems to be essential for holding galaxies together. And the remaining 70% is even stranger, dark energy, a mysterious force that's accelerating the expansion of the universe. Now, these concepts, dark matter and dark energy, weren't invented on a whim. They're hypotheses supported by very real observations. Galaxies rotate too fast to hold themselves together with just the gravity of their visible matter. Galaxy clusters behave as if they have far more mass than we can see, and the expansion of the universe isn't slowing down as it should because of the mutual gravity of all the matter. Instead, it's accelerating. All these observations are real and need explanation. Dark matter and dark energy are the explanations we've constructed. But here's the deep philosophical problem. We're saying that 95% of the universe is made of stuff we can't see, we can't touch, we can't directly detect, and whose fundamental nature we don't understand at all. It's like being a 19th century doctor and not being able to explain why patients were getting sick after certain surgeries. So you invent something called miasma, an invisible influence that causes disease. It works as a temporary explanation, but it's not real physics until Pasteur discovers bacteria. We're in a similar position with dark matter and dark energy. They're cosmological miasmas, explanations that work mathematically, but might be pointing towards something completely different that we don't yet understand. And there's a fascinating story here that many people don't know. When Albert Einstein developed his theory of general relativity in 1915, he discovered something unsettling. His equations predicted that the universe couldn't be static. It had to be either expanding or contracting. But at the time, everyone, including Einstein, firmly believed the universe was eternal and static. So Einstein did something extraordinary and questionable. He added an extra term to his equations, a cosmological constant specifically designed to counteract gravity and keep the universe static. It was an elegant but unnatural solution, like a mathematical patch applied to reality. Years later, when Edwin Hubble discovered that galaxies were indeed moving away from each other, that the universe was expanding, Einstein called his cosmological constant his biggest blunder. He removed it from his equations. But here's the ironic twist of history. It turns out Einstein wasn't entirely wrong. We do need something very much like that cosmological constant to explain the accelerating expansion of the cosmos. Dark energy behaves mathematically almost exactly like the cosmological constant that Einstein introduced and then discarded. He regretted it too soon. But even this revival of his idea doesn't solve our fundamental problems, because we still don't know what dark energy physically is. We just know we need something with its properties to make the equations work. So, where does all this lead us? There are cosmologists proposing something radical. What if the Big Bang wasn't the absolute beginning? What if there was something before? There are theoretical models called cyclic cosmologies that propose the universe goes through endless cycles of expansion and contraction. Imagine a cosmic heart that beats. Each Big Bang is simply the rebound from a previous big crunch. Each universe is born from the ashes of a previous one. It's a philosophically beautiful idea because it eliminates the awkward question of what came before time. There was always something. Time becomes cyclical instead of linear. Other physicists are proposing something even stranger. String theory, which attempts to unify all the fundamental forces of nature, predicts the existence of extra dimensions of space that we can't perceive. In some string theory models, our three-dimensional universe is a kind of membrane floating in a higher dimensional space. The Big Bang could have been the result of two of these cosmic membranes colliding. Our entire universe would just be a ripple in a multidimensional ocean that we can't see. It sounds like science fiction, I know, but these ideas are supported by deep and rigorous mathematics. The problem is, they're extremely difficult, perhaps impossible, to test experimentally. Which brings me to the most important point of all. We're at a moment that hasn't been seen in cosmology since the days of Einstein and Hubble. A moment where the empirical data is outstripping our theoretical ability to explain it. The observations are saying something that our theories can't accommodate. And this isn't a crisis, it's an opportunity. This is exactly how science advances. Newton built a physics that worked perfectly for objects moving at normal speeds. Then Einstein showed that at speeds approaching the speed of light, Newton's equations broke down. Not because Newton was wrong, but because he was incomplete. His laws were approximations of a deeper reality. We're at a similar moment now. The standard model of cosmology isn't wrong. It's incomplete. It's an approximation of something deeper that we don't yet understand. And let me be very clear about something. This uncertainty doesn't mean that science is failing. On the contrary, it means that science is working exactly as it's supposed to work. Science isn't a set of dogmas written in stone. It's a process of constant refinement, where each generation builds upon the work of the previous one, correcting errors, expanding understanding, asymptotically approaching a more complete picture of reality. The scientists who are measuring the Hubble tension aren't destroying cosmology. They're saving it from complacency. The astronomers who are pointing out impossible galaxies in James Webb's images aren't sowing chaos. They're pointing the way to a more complete physics. Think of it this way. Imagine you're a cartographer in the age of exploration. You've created beautiful and detailed maps of the known world. Every coastline, every mountain, every river is carefully charted. Your maps work perfectly for everyone who sails the known seas. And then one day, an explorer returns from a voyage and tells you there's an entire continent that isn't on your maps. Does that mean all your previous maps were useless? Of course not. They were accurate for the territory they covered. But now you need to expand your understanding. You need bigger maps. That's exactly where we are in cosmology. The old maps worked for the territory we knew. But now we're seeing new territory and we need new cartography. The next few years are going to be absolutely fascinating. James Webb is just beginning its mission. It's going to keep looking deeper, farther back in time. It's going to find more impossible galaxies. It's going to raise more uncomfortable questions. And those questions are going to force theorists to develop new ideas, new mathematics, new physics. Maybe we'll discover that dark energy isn't a constant but changes over time.
Maybe we'll find direct evidence of dark matter that finally tells us what it is.
Maybe we'll discover that gravity works differently at cosmological scales than we thought. Or maybe something completely unexpected, something we're not even considering right now. And here's the beautiful part of it all: the discomfort, the uncertainty, the contradictions. They're not signs of failure. They're signs that we're at the edge of human knowledge. They're signs that we're asking the right questions. Every major breakthrough in physics started exactly like this, with data that didn't fit, with experiments that gave impossible results, with theories that broke down under the weight of new observations. And each time, after years or decades of confusion and debate, a deeper, more beautiful understanding of how reality works emerged. So, when you hear that the standard model of cosmology is in crisis, don't interpret it as the end of something. Interpret it as the beginning of a new era where our understanding of the universe is going to expand in ways we can barely imagine. We're living at the exact moment where the universe is whispering secrets that we can't quite fully understand yet. And that's perhaps the most exciting position a human being can be in, on the edge of mystery, looking out into the unknown, with the tools to finally start deciphering it. The universe isn't broken. Our equations are incomplete. And that's exactly what makes this moment so extraordinarily beautiful, because it means there's more to discover. There's always more to discover. And that's the very essence of why we do science.